Oh. Okay. Cool. Let's try to dim the light. Probably better. So we add a new layer to our language, the expression language that we introduced last time. We move on and add new constructs to it, and the resulting language is called simple. All right. It's a very simple language, as you might expect, as the name says. We're going to talk about two aspects, right? The language and its dynamic semantics today. We're going to talk about static semantics and compilation next time. And in talking about the language, we're going to... Oh, come on. All right. We're going to talk about syntax, syntactic sugar. So that preprocessing step there is going to be concerned with syntactic sugar, which is a concept you might be familiar with. We're going to look at a few simple programs, examples, and we're going to introduce the abstract syntax tree that will be useful for your lab. Throughout the entire discourse, we will consider programs and their abstract trees one and the same thing. We're sweeping under the carpet the aspect of parsing. As I said last time, it's not something that we find very useful to teach, because one, there are very good tools available, and on the other hand, those good tools rely on very sophisticated algorithms that we wouldn't have time to cover, or if we would cover that, we wouldn't have time for the more interesting stuff that I have chosen to present here. What are we going to add? Very simple stuff, right? Built-in conditionals, so if then else, and function definition and application, so how to define a function, how to apply a function, and recursive functions. And with these elements, we would have a Turing complete language at this point, right? Notice that for Turing completeness, we don't need while, we don't need for, right? All we need to do is to have is recursion. At which point, right, we actually have enough to study virtual machines, study execution, right? It becomes a very interesting vehicle for looking at the execution of programming languages. One element of this language, which we didn't have in expressions, is explicit types. So we're going to have to specify the type of an expression inside the language. So since types are part of the language, we have to define the language of types. All right? And last time we defined types, but in the context of finding out the type of an expression, right? The expression language didn't say anything about types. Types were just a semantic concern. So here, types become a syntactic concern as well. Okay? But the types are the same. So we're going to have the same kind of rules, right? Int and bool are the elementary types, right? The ones that we can construct from, because our expressions, our language, is going to be concerned only with integers and booleans for the time being. And since we were saying that we would introduce functions, right, we need a type for functions. And this type, if you have any previous exposure to a Camel, you should be familiar with T1 arrow T2. If not, you should know this type from mathematics, right? This notation from mathematics, we used to say that, right, a function f is defined on a domain A and a codomain and a range B, right? B was the range or the codomain. And this notation essentially is the type of a function, right? We're saying that an arrow right, represents a function taking values from the type T1 and returning values from the type T2. So in our language, if T1 and T2 are valid types, then T1 arrow T2 is also a valid type. This is what the rule says. These inductive rules are simply defining the language of types. So, at the level of OCaml, right, last time we have introduced the abstract syntax tree for expressions. We also need to add an abstract syntax tree component for types. All right, and it's a very simple type. Now, you may think that this notation is magic. I definitely, when I first saw typed languages, and especially functional programming languages with types, I thought this is magic, right? Because it hides a computation inside, and it's something very esoteric. But actually, this is just a pair, right? We're just saying that we are taking values from A and returning values from B, right? So it's just a pair. If you think of a function, actually, ultimately, what's the function? It's a set of pairs, right? If if I say x goes to x plus 1, right? Lambda x. Okay, let's put a lambda here. Maybe you are more familiar with the lambda notation. Lambda x goes to x plus 1, right? This seems like a computation. But I can think of it as the set of pairs if I think of natural numbers, right? Set of pairs, 0, 1. So input 0, output value 1, 1, 2, 2, 3, right? So this computation is just a map. I input 0, I return 1. I input 1, I return 2. I input, and so on and so forth, right? So this entire set of pairs, that's what the function is, right? The arrow is just beautiful notation, but it's still a pair between A and B, elements of type A and elements of type B, right? Obviously, we will never want to represent the map internally as the set of all pairs. We want the computation. That's a lot more compressed, right? But semantically, we can think of it as the set of pairs. We can think as if the set of pairs is already available. I have infinite storage, right? And I don't have to think about a computation that goes on. Okay? So from a semantic point of view, this helps very frequently. And in that case, it shouldn't be a surprise that what we have here is just a pair of two types, right? The type of the input and the type of the output. We're qualifying this pair with the keyword arrow, but we just have a pair. Cool? And the language of expressions which we're familiar with, right? These are rules that you've seen last time. I'm not going to spend too much time on them, unless there are any questions. No? Cool. And let's introduce the new types of expression, new kinds of expression. Now the word type is very overloaded, right? Because if I say a new type of expression, that may be confusing, right? Do I mean an actual programming type or just a generic a generic kind? So I'm going to try to use kind as much as possible, but if I forget, just try to derive it from the context, right? So, two new kinds of expressions, conditionals and function application, and then there's function definition on the next slide. So there's three new kinds of expressions. The first rule says if E1 and E2 are valid expressions, right? Then if E, then E1 else E2 and is a valid expression. And notice that we're not saying anything about the requirement that E should be a Boolean. All right? E necessarily has to be a Boolean, but that is going to become part of the static semantics. As we did last time, right? We try to see whether we have a type checking mechanism that tries to see whether an expression is well typed, and whenever E doesn't have the type bool, that is going to fail, right? At the syntax level, we don't worry about that concern right now. E1 and E2, again, there's going to be another concern. E1 and E2 have to have the same type, right? Either both integers, or both booleans, or both functions from the same type to the same type, right? So notice that if is polymorphic. The type of, whenever we get there, the type of E1 and E2 has to be the same, but doesn't have to be fixed. It's not known up front. Okay, now, are there any questions here? Cool. Function application. So we use the curried notation. We discussed about curried notation at some point, right? We don't like tuples. The very typical notation is in math would be like this with commas. Sorry, not there, here. Comma, comma, and another comma, right? So we're not using that. We're thinking of this space in between as an invisible operator, invisible infix operator. And we're saying that E is applied to E1, and that produces a function which can be further applied to E2, and that produces a function which can be further applied to E3, and so on and so forth up to En, right? So the rule essentially says that if E1 up to En are valid expressions, then so is bracket E applied to E1, E2 up to En, close bracket. And we're making the bracket part of the syntax. We're making it compulsory, right? Now, again, there's a typing constraint here, but we're not worried about it, because if this E, right, if this E has type T1, arrow T2, arrow and so on and so forth, arrow Tn, arrow T, it must be the case that the type of E1 is T1, the type of E2 is T2, right? So that's a typing constraint. Again, that's going to come up later. Cool? Any questions here? Everybody seems very familiar, suspiciously familiar with this. Have you taken the class before? From somebody else? All right. Function definition. So we know how to apply a function. And we want to know how to define a function. The function definition is a bit weird in terms of syntax, right? In many languages, we have to provide the type up front, right? It so happens that OCaml as a language is very advanced and can infer types. So most of the time, we don't need to say what the types are. But in many languages like Java and C#, we have to say what the types are explicitly, right? And what the compiler does is only type checking. Type checking is obviously much simpler than type inference, and we're going to limit ourselves to type checking here. Therefore, we're asking for the types to be provided up front. This is why at the very beginning I was saying that types are becoming part of the language, because we are using them here. We declare the types of our functions with a very weird syntax, but one that simplifies our parsing, because we have implemented a parser which you are going to be using in the lab, and it's easier to parse with this syntax than with any other syntax, any of the common syntaxes that are typically used in programming languages. So I'm going to put a type here, right? I'm going to have this fun keyword that opens the definition of a function, and the first thing I put inside is the type inside curly braces. So you might hate it, you might not like the notation. I'm not a big fan either, but it works for us, and it provides a good vehicle for teaching type checking. All right? And then everything looks pretty much like a lambda. I have a list of variables, right? Arrow, and an expression that contains those variables. Okay? So We're going to see examples very soon. All right. The variable names x1 up to xn have to be pairwise distinct. No symbol can appear twice, right? Because they would be indistinguishable otherwise. And we want to have, well, in this case, we want to have at least one argument. Okay? Since it's not a lazy language. If it were a lazy language, we could entertain the case when n is 0. Now, there's another definition down there, but let's take a look at this one. Is everybody okay with this definition? Cool. Let's look at an example. Let's look at a few examples. I'm going to get to the point where we define functions, and then we're going to go back to the recursive function. So these are very clear examples. You wouldn't have any doubt. And we have the prefix notation as we had it last time, and we're going to use it as a shortcut for the abstract syntax tree. All right. Whenever we talk about functions, right, what you should think about when you see the arrow is an operator. It's a strange operator because it's an operator between types, right? You can think of types as objects. They're not, in our language, they're not really first-class objects, because if they were first-class objects, they would be allowed as arguments to a function. So we're not that far. There are languages where this is possible, and the type is a first-class object. Anyone knows an example? Even a COCAML is to some extent, because a type can become an argument to a module or a functor, right? If you have gone that far. But one language where this is prevalent is Haskell, and that has also been imported in recent versions of Scala. So there are a bunch of languages there where we can do the so-called type-level programming, which is extremely powerful in creating generic libraries. So the arrow is an operator, and whenever you see two arrows side by side, the question is, how do we associate the operator? For a very well-known operator like plus, we know it associates to the left. If I say 1 plus 2 plus 3, right, first we should operate on 1 plus 2, and then the result of that should be added with 3. So how should we associate here? Well, you see it on the slide, it's right associative, so we should associate here, right? This is what we should consider first. This makes total sense, right? Why? Because if I have a function f(x, y) defined as x plus y, and I'm using a bit too much of Haskell syntax. You can tell that I like Haskell more than COCAML. But nevertheless, so let's say we define this function, right? And I apply this function to 1 and 2. Okay? Now, I was saying that the space between these syntactic elements is an operator, which we call apply. So, and this operator applies to the left. So I have an operator, an invisible operator here, an invisible operator here. I associate like this. Application associates like this, right? So first I apply f to 1, and the result should be a function that I can further apply to 2 to get a result, right? So let's look at this type, right? So when I apply f to 1, I have consumed this. What do I get? A function that is capable of taking another argument and returning a result. So the result of the first application is a function, right? Which is why the natural association is to the right. Whenever I write the arrow without any brackets, right? I have to think of it as this is the result of the first application. So this is my grouping. If it weren't that, if I would say, oh, let me associate here, let me associate to the left, then the first argument to the function should be another function. If I'm putting brackets here, whenever I apply f, the first argument should be some g, some function g, some function g whose type is int to int. That would be the syntactically correct form. So it makes sense to have this associativity. Remember that we're still in the realm of syntax, right? But whenever we reach the semantics, this will become prevalent, right? I'm just trying to explain now why this kind of associativity is the right one to have. And this essentially argues in favor of language design, right? Languages have to be well designed, have to be designed in a way in which they are convenient to the user. The right associativity is what the user wants most of the time. All right? Surely there will be cases when the left associativity makes sense, but probably much fewer such cases, right? Therefore, we take the route that is convenient to most people. So let's look at a definition of a function. All right? Because some of you were squinting their eyes when we introduced the formal notation. So now you have an example. All right? So this is a function definition. It's a function that adds two values in our language, right? It looks a bit hairy, right? But we could have written it in a much more contracted form. So notice that here, essentially what we have is two functions. The outer one takes an argument x, right? And returns another function, explicitly returns another function, which that function, that inner function, takes another argument y and returns x plus y. We could, of course, have written this as fun, int to int to int. I'm just going to write I for as a shorthand, x, y, and we get x plus y, end. Right? So we don't have to write two nested functions to achieve the same thing. We have a notation that allows us to do exactly that. But just to show what's possible with our language, we show that notation. Is it clear? Cool. All right. Back to recursion. Yes?
So all our functions are always going to take only one parameter?
No.
As in anything that's bigger will be composed of functions that can transform between each of the parameters.
No. So I just showed you the contracted form.
Yeah, but it's still int to int to int, right? So there is a function that does. I mean, that it's basically the same thing as this. Right?
Yes. So semantically it is, right? So make no mistake, no compiler is going to translate a function of two arguments into one that takes one argument and returns another function, right? Because that's very expensive, and compilers can optimize that away very, right? For us, for the purpose of defining a semantics, it's easier for us to do it this way,
Rather
right? To think of it this way.
A pair of, and then we put I.
Again?
As in the other way of denoting a function that takes two parameters and then returns the output as one is like putting int, comma, int in a pair.
Yes, you could have that. We haven't introduced pairs yet.
Oh, okay.
So, and that will come, yeah. But if we had pairs, if we had constructions and essentially data structures, we could use a pair, and we could say x comma y, and have a function of two arguments, right? Which two arguments actually are a single argument combined, having two components, right? But yeah, very good. That's a good observation. But I mean, don't be fooled into, and whenever we're going to use our toy compiler, we will follow that route of a function that returns another function, right? But compilers don't do this. It is often argued that functional languages are slow because of that, but not anymore. It's been 10, 15 years since these problems have been solved on an industrial scale, and we have very good compilers for functional languages. The second example, we haven't looked at this one, and maybe it's worth looking at it, right? It's where we associate to the left explicitly, right? We use brackets here, to associate to the left. And then, what would be a good way to define this function? Well, the argument to this function should be another function, f. Note that this is an anonymous function. This is an expression. This is an expression that doesn't have a name, right? We don't know how to give names to things yet. It's an anonymous function, right? It's just a lambda. This fun here is the equivalent of a lambda in the lambda calculus. Okay? Everybody's comfortable with that, anonymous functions, right? In the 4th year. I would expect that. So the argument to this is another function called f. Then the type of f that we have here, the type of this f should be this one, right? Whatever is before the topmost arrow, right? And then, what can I do with this f? I can only apply it to another end. So I can only do something like this. Right? I apply f to 2. At this point, the result of this has to have this type, right? Right? Which justifies us in the result of the entire function having this type. So we're also noticing that these two types should be the same. I'm jumping the gun, or I'm introducing slowly the concepts of type inference. At some point, we're going to talk about that, right? Yes? What do you mean the same function? No. So f should be the type of f is the first argument, right? Let's say I say x here, x and x, because I can rename. Does that make things clearer? Yes? So, this is T1, this is T2, right? So I have a type, but my type is structured like this. Something here, and I call this T1, and this here I have T2, right? So the type of this x should be T1, which is this. Clear? No? How about what? X and 2? So the type of this x is int to int, right? So the type of this x is int to int. Therefore, it can take an int, which is the 2, and will return an int. Okay? Come to at the end of class. Recursion. All right. The story about recursion. How much time do we have? Let's see. Has anybody heard of the fixed point combinator, of the Y combinator? You must have heard of it because there's a site called by that name. But do you know what it stands for? What's a fixed point? In algebra, what's a fixed point?
Fx equals x.
Good. All right. So fx equals x. So if I have some function, right, I take the first bisector, and it intersects the graph of my function here. So this is the graph of x, this is y equals x, right? And they intersect here, and this is a point where fx equals x, right? And if f is very complicated, say it's an exponential kind of function, we won't have an algebraic solution for it. We don't have an expression for the solution. So typically we have a process of approximation for finding this solution. And how does that work? In a very simple manner, and I'm oversimplifying here because this function needs to have very strict conditions for this to happen, but we're not a calculus course and I'm trying to give you an intuition, right? I pick a random value and then I do this. Let's change colors. And I'll never reach the point, but I'll get as close as I want, right? So this iterative process is expressed by, this is the value x0 that I pick randomly, let's say, right? Or maybe not so randomly, but we can't always pick, we don't always have a scientific way of picking it, right? So let's call this x0, and then I'm going to have x1. x1 is f x0. x2 is what? f x1, right? x3, so xn is going to be f xn minus 1. So I can go there, I can do this ad infinitum, right? So I have an iterative process of finding the fixed point. And why is this a fixed point? Well, if I say that xn is f xn minus 1, and the f has some conditions like it's continuous, for instance, then I will have that lim xn equals f of lim xn minus 1, right? I could say a lim outside because of continuity, the lim outside commutes with the f, right? And then lim of xn and lim of xn minus 1, they are the same, right? So definitely the limit of this sequence is the fixed point. Okay, that's the argument. All right, keep that in mind, because what I want you to understand is this iterative process. This solves this equation, right? Which I could write as x equals fx. So let's remember it in this form. Now, let me write Fibonacci in a mathematical form. Not Fibonacci, factorial. It's easier, right? So I'm going to say that factorial of n equals 1 if n equals 0, and let's put the n first. N times factorial of n minus 1 otherwise. Okay? I'm going to remove the n from here. I wish I had a eraser, but we're removing this from here. I'm going to put the lambda n in front. Lambda n, anonymous function, everybody understands what that is, right? So if you look carefully at this thing, this is a big function g of f and n, right? But actually I can look at it as a function, big function g of f, because the lambda n is inside. F is free, right? G of fact, right? So now what I want to do, what this definition says is that fact is g of fact. Do you see a resemblance? Previously I had x equals fx, right? So look at this as an equation. We're very used to looking at this as a function definition, right? Recursive function definition. It's an equation, right? And yes?
What is the meaning of g?
G is this expression, right? In this expression, fact appears free.
I mean, G is which expression?
That entire expression is I denoted by G, right? Fact appears free, so therefore fact should be a parameter to G, right? So when defining a recursive function, we're actually solving an equation, a fixed point equation, right? How do you think it's solved? Well, we need to define a space of approximations on functions, right? So my space of approximations is going to be in the following way, right? I'm going to add to my space of values, which is currently integers, the value undefined, which is also called bottom sometimes, right? And a function, if a function is defined in more places than a previous function, then that function is more precise. I can start with the function that is defined in no places, right? So I can call it an f0, right, such that f0 of x equals bottom everywhere for all x's. If I plug this f0 into this argument, I am going to get a function that is defined in one place. So it's going to be the result g of f0 is going to be defined in for n equals 0, right? And undefined for the rest, because that function, that undefined function is going to be plugged here, and undefined times anything is undefined, right? So let's call this f1. Now gf1 is going to be what? It's going to be a function that is defined in two places. It's first of all defined in 1 for n equals 0, and also it's going to be defined for n equals 1, right? Because when n equals 1, I get n equals 0 here, and this f0 is defined, this f1 is defined for n equals 1, right? So if I do this process and I have fn equals g fn minus 1, I'm going to get better and better approximations of this function. I'm never going to get the factorial function. But guess what? We're interested in factorial of 100. So if I have f101, that f101 is defines factorial for values from 0 to 100, and it's undefined for the rest. If for the purpose of computing 100 factorial, that function is good enough. So I'm only going to need the first 100 approximations to compute 100 factorial, right? This is what really happens in recursion, semantically speaking. Okay? Now, here's the absolute. So this is just, setting some background. It's not really material that you have to learn for the exam, right? I'm just trying to provide some understanding. Here's the absolutely fantastic news. The solution for this equation, which in algebra is not always available, is always available in the lambda calculus. There is a combinator, a function, that can extract the solution to any g. And that combinator is called we just mentioned it, the y combinator, right? The fixed point combinator. So there's a combinator which we call mu, such that mu g defines the fixed point of that g. Okay? So I'm going to open Chrome. And I'm going to go to Rosetta Code. And I'm going to look here for the Y Combinator. You know what Rosetta Code is, right? It's a site that collects programs for famous problems in all possible languages. So this Y Combinator is in principle can be defined in all languages. And since we're using OCaml, let's look at OCaml, which is here. Okay. So I don't need you to understand I mean, it's a good thing to understand, but we don't have time to talk about it, so you feel free to look offline. There's this definition here of the fix. There are several definitions, as a matter of fact. They're quite complicated, right? But let's look at how, assuming that this exists, right? Assuming that this exists, it can be even a primitive of the language, right? Look at how we define factorial, right? So this is my G now. The G that we were talking about, this is it. Is this clear? So that's a function that is not recursive. Does that make sense? Neither is the fix. If you look at the fix is not recursive. But I want you to focus on this, right? And absorb it a little bit. This is the G that I was talking about on the previous slide, right? It's a function where f, right, is an argument, and what I'm going to want to find out here, what I want to find out here from here is the solution to the equation not fact, let's call it just f. F equals fac f. I want the solution to this equation. This is what I want as my factorial, right? And the good news is that if you look here, this is automatically computed by fix. So this is equal to right? So what do we take from here? Is this clear? Does this make sense? Looks like a lot of magic. But, you know, I mean, if you ever consider passing Google interviews and all the, you know, very famous companies, the ones that have very tough interviews, the fixed point combinator does come up every once in a while, especially if you go at a very advanced level. So these things are worth understanding. That's what I'm trying to say. But my point is different. One, recursion is not necessary. We're thinking, you might have been told that what we need for computation, what we need for Turing completeness in a functional language is conditionals, right? Values, expressions, conditionals, and recursion. Turns out we don't need recursions at all. We need to be able to define functions, but we don't need recursion at all, right? I can compute here factorial without any recursion. It's clear, right? So this is a definition for factorial where I don't even need to define a symbol. I can take this fix and apply it straight to this entire function as an anonymous function, right? This clear? So that's point one. Point two, assume now that fix is a fix is a predefined construct. So what kind of syntax would we have to define recursive functions? This is sort of recursive functions, right? So I would write something like fix, right? And then I would use something like this, right? So I have to use a lambda f for that, right? So I have to use a lambda f. So I would say inside here a lambda f, and then I would say a lambda n, right, which is the n that you see here. This is the argument from an OCaml perspective, and then an expression, right? So fix lambda. So I need a keyword to define the fix. I need a keyword for the function that represents the fixed point. This is the function that is being defined recursively, right? I need a keyword for that. I need to specify. And then I need the rest of the function. So now we're going to go back to the slide. And we're going to see these elements. They're called differently because the language designers have had different taste, different personal opinions on what things should be called. But you will see these three elements, right? This part, and then the rest. Okay? Are you ready for that? So, in our slides, okay, we decided to call the fix recfun. We have to say which function it should be the fixed point, right? And then we have the function that takes the integer argument or a bunch of arguments, and what we seek from this is the fixed point of f. The fixed point of this expression, which is f, essentially, right? Does that make sense? People generally have trouble understanding this construct because there's an f in there. Okay? So what I would like to make sure you understand is that this construct makes sense, right? It's a way of specifying that we want the fixed point of a function whose argument is f. Is that clear? So the expression here essentially will not only have f inside. So to you, inside here there's an f will appear inside there. That will seem to you as the recursive call. Okay? But besides f, you also need to have the arguments x1 up to xn. If you look at what we discussed previously, we have the argument n when we construct factorial. Right? So when we say that this is recursion, this is not really recursion. This is a fixed point computation that we're hiding in there. Okay? But it works as if it were recursion. Clear? This is going to take you a while to wrap your head around. So now, what should be the type? Let's try to make sure that the type makes sense, right? So what we need to put in here is only the type of this. All right? Because that is the thing that is called f. Okay, so I'm changing color. So this thing and this thing are expected to be one and the same thing at the point when the equation is solved. Therefore, f should not contribute to the type in any way. Is this clear? Okay. So one thing we can do after you finish the class is go and play with the fixed point combinator. Copy it into a camel environment and convince yourselves that. As a side, so fun coding. Let me see if I can do this very quickly. Let's try JavaScript for a change. If I can get a console running very quickly. Hi. So there's a console somewhere. So let's say I want to compute factorial of 100 or whatever without recursion and without bothering to define something like the fixed point combinator. Have you ever tried that? So let's apply the thing that we just saw, right? So I'm going to define a function. Everybody's familiar with? And I'm going to take another function and some n as an argument. And in here I'm going to say if n equals 0, then 1 else. And this is going to be the kicker. I'm going to call f. What should be the first argument? Pardon? Well, if I only call fn minus 1, where I'm going to get f from? So how about I call f and n times n minus 1? Yes, that's very good. And n, and we're in JavaScript, so we should say return, right? And probably a semicolon here and a return here. So this is an anonymous function, right? And I can close it. And now immediately I can call with some arguments. What would be the first argument? I don't know JavaScript well enough, so for protection I'm just going to put another round of brackets here, just to be on the safe side. What should I use as first argument? How about this entire thing? Everybody can see where I'm going? Does Ctrl plus work? Oh, okay, it works. Good. So I just took the expression, the function that I defined anonymously, and I made it its first argument. Right? And I copied it in here. And then I'm going to say 100 here, because I want the factorial of 100. Of course, it's JavaScript, I'm going to get errors. Right? Everybody is seeing what is going on?
You multiply by a smaller number? Maybe a factorial is smaller.
Yeah, maybe we just do 10.
Yeah.
No, but so, I mean, I said that without recursion and without using anything, and 10 numbers you could actually multiply by hand, right? So I want to make the problem complex enough so that you need a programmatic solution. So you see, in recursion, what does recursion do? It performs this duplication automatically, because copying code is bad, right? You should avoid to copy code. But if you don't have recursion, you can still avoid. You can still do stuff by just duplicating things by hand. All right.
But this is not type safe.
We can get to a type safe. I didn't want to waste much time. We can get to a type safe. No, I mean I'm trying to explain the notation for recursion that we reached at, right? So why do we need the f inside there, right? So I was trying to explain that. Anyway, it's going to be in the recording. That little trick, play with it. I would say it's a good thing in understanding recursion. It will give you a bit more insight. All right, so we talked about this, and let's talk a bit about syntactic sugar. So we have reached a point where we have a core language. So this language is sufficient it's essentially Turing complete. It's sufficient to define any computation, right? But for convenience in general, we want constructs in the language that will make coding easier, will make the code more readable, right? We would want features such as ability to name expressions, right? Instead of having very long expressions, I want to decompose it in small pieces, give a name to each of them, and then use the names, use the symbols in our computation, right? So this is what we call syntactic sugar. It's not a core feature, And it can be implemented by translating it to the core language. So we don't really need to compile that. We need to subject the program to a pre-processing step that will get rid of all the syntactic sugar. All right? And this is what we mean by pre-processing. There are many types of syntactic sugar. You might be surprised to know that, for instance, while can be implemented as syntactic sugar, while as a construct, all the repetitive constructs, because we have recursion and we can always define an auxiliary helper function that is tail recursive and performs the iteration that we need. The one feature of our language that will be implemented as syntactic sugar is let. All right, which is similar to a camel, just that since we don't have type inference, we want the types to be specified up front. So we keep this type annotation in curly brackets associated with every symbol. So you'll notice that every time we define a symbol, like a function, right, we associate a type with it, annotate it with a type. So we would have the let construct take the form x1. Question? Okay. x1, new symbol, completely new symbol, is assigned expression e1, and so on and so forth. Some symbol xn is assigned expression en, right? The types t1 up to tn are the types of e1 up to en, right? And then we have a body. We have a body for this, which is syntactically is that expression, and inside x we can use the symbols x1 up to xn. Right? It's pretty straightforward. We used to do this kind of thing in math all the time, right? So this is the body between in and end. We would denote, we would put names on expressions and then use those names subsequently. So guess what? This doesn't need to be, we don't need a rule for it, right? We don't need to compile it. All we need to do is translate it into a more basic syntactic construct, which is the one given here, right? This one. So instead of having the let expression, right, we can define a function with expression e as body. x1 up to xn, the symbols that previously were names now are argument names, parameter names, all right? We know very well what the type of this function will be because we have the types from t1 up to tn and t, right? And then once we have this function, we can apply it to e1 up to en. So clearly the two expressions perform the same computation, right? They're equivalent. Yes?
I don't understand the light T1. It seems that the T2, T3 up to Tn is missed.
What do you mean?
Like in the function, when you do a syntax sugar translate into T1 up to Tn, but up there I only see T1 as 1 equals to E1.
No, so you also see Tn, right? So you can imagine that there's T2, T3 in the middle, right?
It wasn't linear T1 there.
So they are separate blocks. All right, let's try to write this more clearly. Normally, maybe we would write let on separate lines. T1 x1 equals e1, and then T2 on a separate line. x2 is e2, right? And so on and so forth. So you can imagine that there's a new line here, separating the first binding from the next bindings. Oops. Is that clear? Because we would be able syntactically to detect the next binding because there's going to be a type there, right? So I'm going to have immediately after this curly brace T2, right? So that will be the start of the next binding. Cool?
Is actually just separate the two different.
Preposition.
Oh, you thought dot 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 was part of the syntax?
No, yeah.
Okay, sorry about that. No, I mean, yeah, it's a fair. Yeah. So the dot 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 is part of the meta language. Okay. All right. Partially applied functions are also allowed, and they are syntactic sugar. So if I have a function with 3 arguments, you can see the type here: T1, T2, T3. Right. Then if I apply it only to 2 arguments, what I should get as a result is a function from T3 to T4, right? So this can be easily converted, right, on the fly into this function, which is a function that takes 1 argument and returns the result. Okay? So partial application can be easily translated into syntactic sugar, so that the compiler doesn't have internally to construct closures, right, and can optimize. How do we pre-process syntactic sugar? Well, this is a point where we get to see a little bit of the abstract syntax tree, and it's a very simple kind of traversal, right? It's a recursive traversal on the abstract syntax tree, and it proceeds as follows, right? So we're not giving you the most important part, which is how do we translate the let, because that will be part of the lab, all right? But the important aspect here to understand is that this entire process is recursive. So we input a tree that has syntactic sugar in it, and we output a tree that doesn't have any syntactic sugar in it, right? And we have to see what type of tree is this. Well, if it's a Boolean, if it's a constant, or if it's a simple variable, there's nothing to do for it, because those cannot contain any syntactic sugar. All we can do is return them as they are. If we have a unary operator, an application of a unary operator, then the argument, right, which is represented here, the argument could have syntactic sugar inside. So we recursively invoke. Notice that we're defining here an helper function that helps us getting rid of the syntactic sugar. So we are invoking recursively the syntactic sugar remover on the argument. The result should be something without syntactic sugar, and then we can reconstruct the original expression by using this expression that doesn't have syntactic sugar. Right? So we're returning the same construct, but the argument no longer has syntactic sugar. If we have a conditional, right, the conditional will have 3 expressions: E, E1, E2. E is the if expression, right, the conditional. E1 is the consequent, and E2 is the alternative. Each of them could have syntactic sugar inside. So we recursively invoke the syntactic sugar remover, get simpler expressions, and then use those simpler expressions to reconstruct the original conditional. Okay? And we return it back. And this goes recursively for all the types of nodes in the abstract syntax tree. Right? With one exception. When we reach the let, at the level of the let, we should actually perform the translation, right? That's going to be revealed later. Is this clear? This type of syntactic recursive syntactic processing will be done quite frequently, right? So it's good to understand this pattern. Let's take an example with syntactic sugar. So look at this at it closely. There's 2 symbols defined in there. About pi, 3 is about pi, and then there's a square function, and then we use that to compute the approximate radius, the approximate surface of the Earth, I think. Could be the approximate surface of the Earth, I think. And let's look at the same function when the syntactic sugar has been removed. All right. So notice that the expression that we had previously that we wanted to compute is now the body of a function where these two are arguments. These two were the symbols defined previously. And then this function is applied to two arguments, which were the values given to the two variables. Okay? And this obviously will compute the same thing. Is this clear? All right. This is a recursive function, the power function. Perhaps what's not very apparent here is that we're assuming that y binds tighter than the function application, which is again not very common in most languages. So you don't need the bracket, but just for making it clearer, we're going to have the bracket there. It's everything you expect, so just look at it to get familiar with the syntax. Right? This is how we write power in our new language. Clear? All right. So remember what I told you. This symbol is equal to this expression, for which reason we can reuse this name inside. However, what's the name of this function? So if I look from the outer level, if I take this as a black box, what's the name of that expression? Do we have a name for it? We don't have a name for it. It's an anonymous function. Right? Which makes total sense, because what we're doing inside is defining a fixed point equation. We're using the power name just for the purposes of solving that equation. Outside of it, we don't leak the power. Okay? So remember that. You're seeing that name power there, you might immediately say, oh, this is the power function. This expression doesn't have a name unless you give it one, right? So you can, of course, at the outer level, you can say let power equals. All right? And then this power outside and this power inside, they won't clash. It's fine. Right? The innermost symbol takes precedence all the time. Seems a bit redundant, right? But this is how the language works. Is this clear? Cool. Higher order functions. Okay. So this is a function that takes two arguments and an operator, and a base case, and essentially applies the operator we have an I'm missing this OPEX, right? So this will perform essentially op x, and so on and so forth, op x iv, and many brackets being closed here, right? And this will happen how many times? Y times, right? The original value of y. So we can have this kind of recursion. It's essentially like a fold. Okay? So we can have a type of iteration. This is not tail recursive, but we can have a higher order function. So here, the interesting thing is that op has this type, right? Op is a function. So I can have a function that is the argument to another function. We have defined a language that naturally allows that. Okay? So we've seen a little bit of this. The abstract syntax tree in OCaml. This is the type that we're going to see in the lab, right? What I would like you to take from this is the fact that one, it represents the language that we defined fully, right? Two, it's recursive, so essentially the programs that we can write are unbounded in size, right? We can write programs as complex as we need. If you look at all the rules that we have defined, inductive rules for the syntax of the language, you will find one clause in here for every rule, right? And that should always be a correspondence. Every clause here, by clause I mean essentially a line or something that is introduced by a vertical bar, right? Every clause here, if we go back to these rules, right? These and this, right? This 3 slides with rules. For each rule, there should be a clause. Okay. Moreover, we are adding rules for the syntactic for syntactic sugars, right? So we're allowing the let to be part of the abstract syntax tree. Any questions here? All pretty straightforward, right? So now, what are we going to do if we want to process a program? Execute, compile. We're going to traverse this tree, right? We'll start at the top. We're going to have a big switch case or a match in OCaml, right? And say, if the node is of this type, do this. If the node is of this type, do this, right? Obviously, we have recursion inside the data structure. So we're going to have recursion at the level of the traversal, right? Every time we go to an inner expression, like here, right, we will have to invoke our processor recursively, right? Cool. So that sets the pattern for all the processing that we're going to be doing. Questions so far? Cool. So, dynamic semantics. Again, we're going to have a bunch of rules, very similar to, actually we're going to reuse some of the rules of EPL. But we're going to have to deal with a few new concepts. So remember, everything is a value. We're working with inside a functional framework. Everything has a value. Functions are values, right? They are computation, but nevertheless they are values. They can be passed in as arguments to other functions. So we always want to find out what's the value of an expression, right? And now we need to introduce a new type of value, a new kind of value. Type, as I was saying, is overloaded. So it's either an integer or a Boolean, right? Or a function definition, or a recursive function definition. Okay. So we're going to start with contraction rules. The first two you've seen before. Okay? And you know what they are. For conditionals, right? The rule is relatively simple, right? I'm going to evaluate, I need to know the value of the conditional, right? So if the conditional is true, then I'm going to use the consequent. Otherwise, I'm going to use the alternative, right? So I'm going to have two separate rules, one for true, one for false. Clear? So the first rule that you see there is for the condition being true, and we have another rule where the condition is false. Okay? Quite straightforward, right? Now, as we start delving into functions, function definitions, we have to understand the concept of a free variable. I think most of you are familiar with it already, right? Most of you understand what the scope of a variable is, right? I define a variable in a language like C, Java, C#, right? We define a variable that is inside a block, inside the nearest open brace, the closest open brace, right? And the range, the scope of that variable extends up to the point where that block closes, right? How about variables that appear inside this scope but are not defined there? Right? If I restrict my view to just that block, those variables are unbounded. I don't know the definition. I don't know where they are defined, right? They're unbounded. Okay? So those we call free variables. Free variables, we have to keep track of them because at some point, as we expand our view, we're going to encounter a place where they are defined. All right? So think of traversing the abstract syntax tree, right? You're going to go down and you're going to come back up. When you're coming back up, from every block, you're going to remember the set of free variables. Variables that have been encountered inside, but for which you don't see a definition. In our context, the definition is the let, or the argument to a function. And you're going to see variables that don't appear to be declared, right? What may happen with those? Well, they may be declared a few levels above, right? So we keep track of them. We have to know what they are, so then we can match them with their own declarations at some point. So, how do we collect the free variables? We introduce a new relation between a program and its set of free variables. This bow tie, right? On the left side, we have the program. On the right side, we have the set of free variables. And we're going to introduce a set of inductive rules, to have such a definition. So, for instance, in an expression 4 times square x, right, we see these symbols square and x, none of which being defined inside that expression. Therefore, they're free. And in defining this relation, we're going to have to find a way to say that these are the free variables. The set of free variables is square and x. Okay? And that's the reading. The set of free variables in 4 times square x is square, the set of square and x. All right? Let's expand the view, right? So we can think of it that, oh well, this is the expression that I'm focusing on right now, but this is part of a bigger block, right? So let's expand our view. So this expression that we're previously limited to now appears inside this bigger block, right? So what do we see inside here? That x is actually defined, right? X is being defined inside this block. X, because of that, is bound, right? The value of x doesn't make sense outside this function, right? Therefore, x is bound. Square, however, is not. So square is still free. So we're going to say that this expression, function of x going to 4 times square x, then applied to 3, right, has as set of free variables square. Is this clear? So typically, as we expand our view to bigger and bigger blocks, right, the set of free variables goes smaller and smaller. Now, you will probably not be surprised to find out that well-typed programs do not have free variables, right? So the purpose of this approach is to create a set of rules eventually whereby whenever I finish with a set of free variables that is empty, I can say whether the program is well-typed or not. Okay? So let's start with the inductive rules. If I have a variable x then the set of free variables is x. If I have a constant, so remember that this is a schema with n. When we say n, we typically represent constants in the meta language. N is part of the meta language and denotes any possible constant of our language, integer constant. All right, same goes for true, which is a constant, same goes for false. Okay, so you're noticing every occurrence of x adds x, every occurrence of fun x, fun where x is defined, x is an argument, is going to remove x. It's going to be like a game where, you know, there's two participants, there's two opponents. One puts tokens in the basket, and the other one removes tokens from the basket. Right. So, for any expression, if the set of variables is x, then if that expression becomes the argument to an operator, a unary operator, the set of free variables doesn't change. P1 doesn't add anything, doesn't remove anything, right? It's a plus or a negation or a unary minus, right? Similarly with binary operators, just that now we have two expressions, right? So we have to combine these two sets of variables. So if E1 has set of free variables x1 and E2 has set of free variables x2, then combining E1 and E2 via binary operator will result in an expression whose set of free variables is x1 union x2. Right? Again, we haven't introduced any variable, we haven't removed any variable, but we have two expressions, so their free variables have to be combined. Right? Notice that the free variables here don't need to be distinct. A variable x may appear in both E1 and E2. For instance, if I say x plus x, that's perfectly valid, right? And x is still unbound, right? X is still free, and it might become bound as we move to a bigger scope. Clear? Cool. Similarly, for conditionals. So just take a quick look. It's exactly the same, right? Now, how do we remove stuff from the basket? So the fun does that, right? Whenever, if I have E as an expression that appears as the body of a function, right? So let's say that the set of free variables is x, and then all these x1 up to xn become bound in this construct. So what do? We remove them from the set of free variables. Question. Is it the case that all of x1 up to xn need to be inside x? No, right? So a function f of x equals 3, that's a perfectly good function, right? It's a constant function, but it's a function whose body doesn't contain x. Right? So I don't have a requirement that all of x1 up to xn appear inside x. Cool? And the same thing with recursive functions, just that here I have an added symbol, which is f. The symbol giving the name, the inner level name for the recursive function. That symbol is also bound by the recursive function definition. Cool? So that's the difference from the previous one. This f appears here, and therefore this f appears here as well. So, how do we compute this? Exactly as we defined the pattern previously, right? We defined a pattern where we traverse the tree and recursively call our helper at every level, right? So we're going to model the list of variables as a, the set of variables, the set of free variables as a list of variables. So what we want to construct is a list. And we start with constants. Boolean constants and integer constants do not have any free variables, therefore return the empty list. If we have a variable, the name of that variable is a free variable, right? Then if we have a unary operator, right? And so notice all these underscores, right? We talked about them. Hopefully, you've seen them in OCaml already. You know they're called anonymous variables, and they're like a wild card, right? They match anything. It means that really that I'm not interested in what's in there, right? It can be essentially here. It can be any of true or false, or it can be any constant, right? Here it can be any operator, either unary, minus, or backslash, or negation, right? So what we're going to do here is recursively apply the function to the argument, because we have said that the set of free variables for the entire expression is the set of free variables for its argument. When we have a binary operator, right, we have to perform union, right? So I'm going to compute the free variables of the left argument, compute the free variables of the right argument, and union them together, right? And here we're going to just concatenate. I think it's concatenation, right? The at, right? So we're not giving. Pardon? List concatenation, yeah. So we're not giving any attention right now. We're not paying attention to repeating variables, right? We can make the variables distinct, right? Take the list into a list of distinct elements later. We don't have to do it at every step. For conditionals, again, the same rule. Compute the free variables of the condition, free variables of the consequent, free variables of the alternatives, concatenate them together. Okay? For function, right, we have to compute recursively the free variables of the body, right? What's here? There's going to be a function name, which we don't care about. There's going to be a list of argument names, right? And there's going to be a
type.
Body.
The first one is the type.
Oh, it's actually the type. That's right. That's right. So we don't care what type the function has, right? And so what we're going to do is compute recursively the free variables for the body, and then subtract the list of variable names. Okay? And similarly for the recursive function. This clear? For application, remember when I have an application, we always have to consider application of one function to its arguments, but every element in that is an expression, right? So I have an application, and the function can be in fact an expression, and the first argument can be an expression, and so on, right? And we can have free variables everywhere. Okay? So the application is pretty much like a multi-nary operator, right? We have unary, binary, but application is like an operator with a variable number of arguments. So we have to take the free variables of the function value, which is E1, right? We're saying that this goes E1 up to ES, right? And we have to take the function E1 is the function, ES is the list of arguments. So we have to take the free variables of E1, and then to take the free variables of every argument, we have to use an aggregated function, which is this list.map. Is everybody comfortable with this one? Everybody knows how it works? It applies a function to every element of a list. Okay? So we get a list of results, and then concatenate applied to that list will flatten the list, essentially. Similarly for the let, All right. So let is essentially like a function definition. Combined with a function application. All right. So we're going to have, remember how the let is translated, right? So we have a function definition inside, and then that function is immediately applied to some arguments. So we're going to have the rules for application and definition, right, both inside this construct. So first we think of the function being defined, right? And we get a list of free variables here. And then we look at the variables being bound, and we have to subtract the variables that are bound from variables that are being defined. Is that clear? Anyway, you'll have plenty of time in the lab to look at this very carefully. All right? It is yet another very simple example of processing an abstract syntax tree. An implementation of the diff method. I thought these were they're not predefined, right? There's this OCaml battery is included that actually has a lot of utility functions.
Sure.
So perhaps we shouldn't burden them with these definitions.
Yeah, some of the libraries may have this code, so you could use it.
Yeah. So this looks at a list as a set and tries to subtract the elements of the second list from the first. All right. Okay. So the next important concept is that of substitution. So we have a piece of code that represents the body of a function. Okay? Just the body. And we have some free variables inside there. We know that it's inside a function already, right? But as you look at just the body, we see some free variables in there. Now, if you think of how function application should work, right? I have to evaluate that body, but in the context of the arguments. So what should we do to achieve that? We should take every actual argument at the call site, and substitute it for the equivalent, the corresponding formal argument, the argument at the definition side. Right? So if I have fx defined as x plus 1, and then I want to compute f3, what do I need to do here? I need to compute x plus 1 where x is substituted for where 3 substitute x. I think this is the standard notation. 3 substitutes x. Right? I have to take the body of f, right, and execute it in a context where that x gets replaced by whatever we want to call the function of. So this thing is very important now. Because what do I want to do? I want to take this entire expression, which may be a big expression, go inside, find all the occurrences of x, and turn them into 3, right? That is what substitution is about. Is this clear? So, we're going to have a new relation. So we have a relation where we have an expression followed by a substitution expression. Right? A substitution expression is a variable and the expression to be substituted by. Right? And then we have the squiggly, which essentially represents the transformation that we're performing, and then we have the result of the substitution. Is this clear? So essentially we're going to say that x times x, when x is substituted by 4, becomes 4 by 4. 4 times 4. Okay? So let's see how this works. If I have a single variable, if my expression is a single variable, all right, then when I replace that variable by any expression E1, all right, I should get E1. Very simple. Notice that V on the outside and V on the inside are the same, right? Now, what if they're not the same? Is that a valid case? Of course it is. We were just talking about a function where the body would not contain the variable, right? So, of course it is. So if I have a variable x and I want to replace the variable v that is not equal to x, that doesn't have the same name as x, by expression E1, right? That doesn't perform any replacement. I still get back x. Okay? Is this clear? Is this clear that we're going to need this kind of case? Cool. So then everything proceeds as before, right? So if it is the case that E1, where whenever V is substituted by E, results in E1 prime, and E2, whenever V is substituted by E, becomes E2 prime, then E1 applied to E2, when V is substituted by E, becomes E1 prime applied to E2 prime. Is this clear? It's very syntactic. It's not looking at what the expression is doing. It's just automatically like hitting search, like hitting replace in your text editor and performing a replacement, right? All right. Similarly, if we have a function of some type, we don't really care what the type is, which takes an argument v and returns e, and then we try to replace v by e1, right? This doesn't have any effect. Why? Because the scope of v is limited to the function. And whenever I define an inner symbol, right, that definition takes precedent. A definition with the same name in the outer scope doesn't have any effect. This is what this rule is saying. Okay? All right, so if I have an expression E and I'm trying to replace V by E1, and if that gives me E prime, and I have that X is not V, and if the set of free variables in E1 is X1, and X is not part of those free variables. Okay? So what does this say? Really, it says that inside here I have an occurrence of V, and V is free. V is not one of X1 up to Xn, right? So I have a function fx equals x plus y. Y is defined somewhere else. All right? So taking this and replacing y with 3 should give me a 3 here, right? If I try to replace x, that shouldn't work, right? But if I try to replace y, that should work because y is not protected by anything. Y is not defined inside. It's free, right? So I should be able to substitute it. I should not be able to substitute free variables, bound variables, but the free ones I should be able to substitute. Okay? Is this clear? Yep. I should be able to change the name of a locally defined variable, right? So f of x plus y, sorry, f of x is x plus y, should be the same as f z plus y. The two functions should not differ in any way, right? So this rule is saying exactly that. All right? So so x must be part of the free variables in E1, right? Otherwise, it doesn't make sense to have it as an argument, right? And essentially, we can change the name of an argument, right? The name x can become the name z, but this is possible only if x is a free variable inside E.
E1.
Inside E1, right? So the case that we have to protect ourselves against is the following. There's a catch here. What if I have f x equals x plus y, and now I want to change this into f y equals y plus y? Is this correct? So this would not be a correct substitution, right? Everybody agrees with that. Okay, so this is the case we want to protect us against. So you see, y is a free variable inside x plus inside this entire expression, right? So then I cannot rename my x with the name of one of the free variables.
You can also rename y to x.
And I can also not rename y to x. Yeah, that's true.
I think
Right.
that one is protecting the y from being renamed to x. Because y was free.
Oh, okay, that's true. Yes, yes. So we can also not rename the y to x. So if I try to do f applied fx equals x plus y, right? So I could in principle rename z y into z, right? But I could not replace y with x. That would also be incorrect, right? So there are these catches. There's protections against free variable occurrence inside the substitution, right? And in the algorithm, we have to take care about that. Okay. So this tries to explain a little bit about name clashes. Okay. Yes. Yes, I'm thinking whether I should stop here. So I think I kind of lost you. I kind of lost you a couple of slides ago already, and everybody is very keen to go.
Tomorrow.
Uh-huh.
I'm not sure whether you finished the whole camera. If not, then tomorrow may be the last chance to try and finish.
Sorry, what's happening at the lab tomorrow?
Okay, so I'm going to